All right, thank you so much for having me here today. I'm very honored to be here. My name is Caitlin Hadrick, and I am a PhD candidate at North Carolina State University, where I'm at the Center for Geospatial Analytics. And when I moved to North Carolina several years ago now, I found out that North Carolina is an agricultural powerhouse. This is a map of the swine confined animal feed operations in North Carolina, and it's unsurprising that we're actually one of the top swine producing states in the union, and we're surpassed only by Iowa and Minnesota. And this is just an example. We also are one of the top 5 poultry producing states. We also are the #1 sweet potato and tobacco producing states. And we also produce a lot of soy, corn, and cotton. And I had no idea about this before I moved there, but when I moved down there, I started to learn about first I learned that we were very proud of our agricultural heritage, but also I started to learn about some of the environmental impacts of this type of intensive farming. And so this is a picture I actually took last year, and this machine is spraying some of the waste onto the field as a fertilizer. It's spraying swine waste, but we also do this with poultry waste. We spread it on the field as a fertilizer. And this is a fabulous way to use the nutrients in the waste to fuel our crop production. But if it reaches our waterways as agricultural runoff, it can have some really negative impacts, like harmful algal blooms, degraded recreational quality, and it's harmful to the benthic organisms, like it can result in fish kills. And so as I'm working on this, I'm starting to think, I'm working with these scientists who are going out in the field and doing a lot of sampling. We start to think maybe there are things that can happen at the field and parcel level, like working with farmers, placing a berm here or a vegetated barrier here, right where the flow is coming off of their field, that would help slow the path of those particles moving from the field and into the waterways. And so in my lab group, we realized we had the perfect tool for that, which is Tangible Landscape, and that's the system that I have here. And so Tangible Landscape, it's a system that has a tangible user interface at the bottom. It's a tangible user interface for Grass GIS. And so above the table that users interact with, we have an Xbox Connect scanner, which is sending its data to Grass GIS, which is a science-based open source geocomputational engine. And so Grass GIS quickly crunches whatever custom analysis you want it to do, and then it projects the results back on the table. And we often make this table out of either CNC routed medium density fiberboard, or we use the fiberboard as a mold for kinetic sand so that you can actually change the topography, change the inputs to the model in Grass, and then project the results kind of in real time. And so this technology has been used in a variety of projects, such as the spread of a plant pathogen called sudden oak death in Oregon. It's been used in a project with residents on the coastal plain of North Carolina and the barrier islands there, and looking at sea level rise. It's been used teaching middle schoolers about geography concepts. It's been used for park design by coupling it with the animation software Blender. And it's even been used to explore subsurface 3D data, like this one here is showing soil moisture. And so we thought this could be a great way to take some of the overland flow modeling tools in Grass and start to play with different mitigation strategies for this runoff. So here's the overland flow algorithm in Grass, which is implemented as rSimWater. And what we've got here is a hypothetical farm field in eastern North Carolina. Right here, this is a swine lagoon where we're storing the waste before we spread it onto our agricultural fields. Maybe this is in the early stages of growing some corn or soy. And then we also have these drainage ditches that are flowing into a buffered stream. There's one right here, and there's another ditch up here that's flowing off into the watershed. And so this model can accept spatially variable inputs. So we can modify the infiltration and the Manning's coefficient to reflect different surface types, which means that we can model how changing land use practices would affect the movement of these particles, and maybe we could slow their travel into the waterways during an intense rainstorm. And so this is actually modeling a 15-minute, very intense rainstorm. Okay, so we turned that into this. This is a real-time, game-like, interactive, tangible landscape activity where those particles are flowing over the surface and they are collecting in the drainages that are now outlined in yellow. And there's a score on the side that reflects how many of those particles at the end of the simulation don't end up in the waterway. And then there's a series of buttons that tell GRASS to update the topography or the add vegetation and then update the animation. And so the first thing you can do with this is decide where you want to place your particles or your fertilizer. And so in this example, our user is deciding to apply fertilizer to the entire field. And then you can go ahead and start playing with the kinetic sand, making things like dry retention ponds, berms, check dams, making additional channels on the field, and then pressing the update button. It won't update how the particles move. That will only update when you press the red button. And then you can also place these red patches, and these patches represent vegetation. And so when the particles hit the vegetation, they will slow down, and they also, some of them will infiltrate into the soil and be removed from the simulation. So they'll also increase your score depending on where you place them. And then finally, we can update our simulation, update the score. You can see that it sensed the patches, and sure enough, this strategy has saved 11% of the particles from ending up in the waterways. And so we've had the chance now to use this activity with a bunch of different groups. For example, this is county government officials in Eastern North Carolina, in one of those counties that had that really high density of swine farms that I showed in the second slide. This is a group of visiting professors who came to my lab group this fall who are playing with it. We've used middle schoolers at a science camp who were learning about phosphate runoff to think about how water moves over the landscape, how it can pick up particles, and those particles containing phosphate, what kind of impacts they'll have on the environment. And then we've also used it with undergraduate and graduate students at the College of Education at North Carolina State and in landscape ecology. And you too can try this out if you would like. It's at the GRASS GIS booth, booth 359 on the other side of the hall over there. And I also want to give a huge shout out to all of my collaborators and co-authors on this project. It's obviously a big team effort. And a shout out to NSF and NRCS for the funding, and a big thank you to the GRASS mentoring community. Thank you.